In this video, we're going to review some important mathematical concepts related to special right triangles, and we'll also introduce right triangle trigonometry. So we see the word right triangle in the title. What is a right triangle? So you know that a right triangle, right, you learned this back in elementary school, is a triangle that has exactly one right angle. You know that the measure of the right angle is 90 degrees. You also learned that the side opposite the 90 degrees is called the hypotenuse. It is always the longest side in any right triangle, and it's always directly opposite the 90-degree angle. The legs are the two sides that form the right angle. Turns out a special relationship exists between the three sides of a right triangle. The relationship is that the sum of the squares of the legs is equal to the square of the hypotenuse. And we say a squared plus b squared equals c squared, and that is the Pythagorean theorem. We use the Pythagorean theorem to help us find a missing side length in a right triangle when two of the sides are known and we are looking for the third side. So now I want to move on to a special right triangle. In fact, this is a screenshot, this little diagram that comes from the Math MCAS reference sheet. They give you this information because special relationships exist among the sides of special right triangles. If you know you have a special right triangle, whether it's a 45-45-90 or a 30-60-90 right triangle, all you need is one side length to determine the other two missing sides. So when we have special right triangles, we typically do not need to apply the Pythagorean theorem. So we'll start with 45-45-90 right triangles. And we have an example of a right triangle here where one of the angles, which is acute, is 45 degrees, and one of the legs is 8 inches long. So because of the triangle sum theorem, that the sum of the three angles in a triangle is 180, I know that that other acute angle at the top is also 45 degrees. And so now I have what's called an isosceles triangle. And the two legs of this right triangle will be congruent. That will also be 8 inches. And if we look up at the diagram, we can see the relationship that exists is the hypotenuse is the square root of 2 times the leg length. So therefore, the hypotenuse of this blue triangle would be 8 square root of 2 inches. So when I have a 45-45-90 right triangle and I'm given one of the leg lengths, I know the other leg length must be congruent and the hypotenuse must be 8 square roots of 2. So then we're going to go on to this pink triangle, which is also a 45-45-90 right triangle. And how I know that is that the two sides are congruent. Therefore, the base angles must be congruent, or 45 degrees. If I know that the side or the leg length is 11, then the hypotenuse is 11 square root of 2. And the other style problem that you'll see, which we have here in green, is a 45-45-90 right triangle where the hypotenuse is given. Now, how do I know these are 45-degree angles? Because those two sides are shown as congruent. Therefore, this is an isosceles triangle. Therefore, the base angles are congruent. Now, let's look at the diagram. How does the hypotenuse compare to the leg lengths? It is the square root of 2 times longer than the leg. Therefore, if I know the hypotenuse, I'm going to divide by the square root of 2 to get the leg length. The leg lengths here would be 9 centimeters each. Let's move on to 30-60-90 right triangles. And 3 of them are shown, along with the screenshot of your Math MCAS reference sheet diagram for 30-60-90 right triangles. Now before we look at the blue triangle, let's look at the screenshot of the diagram. Can you see that there will always be a hypotenuse, right, which is labeled as 2x. There will be a short leg which is always opposite the 30-degree angle, and there will be a long leg, which is opposite the 60-degree angle. If you know the short leg is y, the hypotenuse being 2y implies to find the hypotenuse, you multiply the short leg by 2. So also, if I know the short leg is y, to find the long leg, I multiply the length of the short leg by square root of 3 this time. All right, so let's use that relationship in the blue triangle. First of all, this is a 30, 60, 90 right triangle because the sum of the two angles that are shown is 150 plus 30 more would make 180. So the short leg is given. From there, you should be able to figure out the hypotenuse. It's going to be double 6 inches. We should also be able to figure out the long leg. It's going to be square root of 3 times the short leg. So we've just solved this 30, 60, 90 right triangle. All I was given was one side length. I did not apply the Pythagorean theorem. I simply applied the information from the diagram, from the graphic, onto the right triangle. Let's look at the next example, which is in pink. First of all, there is a right angle in the corner. There's a 60-degree angle, so there must be a 30-degree angle. This time, the side length that's been given is the hypotenuse. So to go from there to find the short leg, I want to divide the hypotenuse by 2. Now that I have the short leg, to find the long leg, I take the 9 inches and multiply that by the square root of 3. Okay, so now we'll go on to our last example here, which is in green. We see that we have a 90-degree angle shown by the little square. We have a 30-degree angle, so the missing angle must be 60 degrees. Therefore, we were given the long side length. To go from there to find the short side length, I want to divide by the square root of 3. Therefore, the short side length must be 10 centimeters. And now you know how to find the hypotenuse. You double the 10 centimeters and you get 20 centimeters. So that's a little summary of how we handle solving special right triangles. Now, so far, we haven't really done too much with angles other than 45, 45, 90, and 30, 60, 90. But we're going to move on to something called trigonometry. And what's nice about trigonometry is you can find in a right triangle not only missing side lengths, but missing angle measures. To do that, we have to be very familiar with 3 sides of a right triangle. We have to be very skilled at recognizing, given any angle, what is the side opposite that angle, what is the side adjacent to that angle, and what is the hypotenuse in that right triangle. So those are our 3 really important sides: opposite, adjacent, and hypotenuse. So first of all, let's refresh our memory, because right now I have 2 sides of a right triangle. I'm missing the 3rd side. We know nothing about the angles, so I can't assume this is a special right triangle. But what I do know is it's a right triangle. So therefore, I can write down the Pythagorean theorem, and I can apply that to this triangle. The missing side length I can call A. B is going to be my longer leg of 8, and C is my hypotenuse, so I can substitute in those values. Now I can square the numbers 8 and 10. Let's subtract 64 from both sides of the equation. So some number squared equals 36. Now the missing side length is not 36. That would not make sense, right, in the diagram. But what number, when you square it, is 36? Let's take the square root of both sides, and we know that that missing side is now 6. So now what I want to do, now that I've identified all 3 sides, is let's identify each side in relation to angle Z. Now be aware, angle Z is one of the 2 acute angles. It's at the bottom left corner of this triangle, okay? I want to know what is the hypotenuse, the opposite side, and the adjacent side to angle Z. Okay, hypotenuse will be the obvious one. It's always across from the right angle. It's always the longest side. Now, I want you to imagine you are crouched in, I don't know, in the corner there of angle Z, and you are looking straight across that triangle. The opposite side then is going to be side XY, and the length of that side is 8. So now that I've identified 2 of the sides, the third side must be the adjacent, or 6. This is the most important skill when we're solving right triangle trig problems. We need to be able to identify the opposite, the adjacent, and the hypotenuse. All right, let's take this same picture, but this time we're going to identify each side in relation to angle X. We'll start with the number 10. Then we'll go on to the number 6, and then we'll look at 8. So what is 10 in relation to angle X? 10 is going to be the hypotenuse, right? What is 6 in relation to angle X? 6 is the opposite side. And 8 then must be the adjacent side. So you want to be comfortable going either way. Either I'll give you the number and you'll tell me, oh, that's the opposite of angle X. Or I'll say, given angle X, what's the adjacent side? And you need to come up with the number of 8. All right, so now let's take this information using these 3 sides, hypotenuse, opposite, and adjacent, and let's think about the 3 main trigonometric ratios. Look at that fancy word, trigonometric, and we usually abbreviate that to say trig ratios. Now, ratio, as you know, is a comparison of 2 numbers, right? So when we're talking about trig ratios, very often our answer is going to be fine if we leave it as a fraction. So what I found on my MCAS math reference sheet for grade 10 is this information. Given this right triangle with that interesting little Greek letter called theta, that's the measure of an angle. It's an unknown measure. So the sine of theta, according to my math MCAS reference sheet, is A over C. The cosine of theta is going to be B over C. And the tangent of theta doesn't involve C, it involves A over B. But your geometry teacher, most books, most videos that you read will give you this little acronym. And my high school geometry teacher said SOHCAHTOA, SOHCAHTOA. And I'm reading down, SOHCAHTOA. Now look at the sign. What do you suppose O and H stand for? Using those 3 words from the previous screen, sine is the opposite over the hypotenuse. Now double check in my little graphic here. Is the sine of theta the opposite of theta over the hypotenuse of the triangle? It is. Cosine then is the adjacent over the hypotenuse. And tangent doesn't involve the hypotenuse at all. Tangent involves a ratio of opposite over adjacent. All right, so now that we have those, and we know that SOHCAHTOA stands for opposite over height, right? Okay, so make sure that you're aware that the O and the H, the A and the H, the O and the A, what that stands for. All right, now let's go ahead and actually find some trig ratios of that previous triangle, all right? So, the one thing you want to be aware of is we never find the sine, the cosine, or the tangent necessarily of the right angle. We're really interested in the sine, the cosine, and the tangent of the acute angles. That's why I only have X and Z for us to look at, okay? Remembering SOHCAHTOA, and I've color-coded here so that my sine, which is my opposite over my hypotenuse, now we want to find the sine of X. So look at that diagram. You're stationed at angle X. If sine is opposite over hypotenuse, what is the sine of X? It's going to be opposite, which is 6, over the hypotenuse of 10. And then we leave it like that. You don't even need to simplify it most of the time. I mean, some websites will make you simplify it, but 6 over 10 is a good answer. I mean, some people want to turn that into a decimal of 0.6. You can, but I'd rather leave it as a fraction because remember, trig ratios, we're talking about fractions. All right, now the sine of z. Now again, sine is opposite over hypotenuse. The hypotenuse stays the same, right? It's going to be 10. But the side opposite z is now 8. So the sine of z is actually 8 over 10. The cosine of x. All right, now cosine. Let's look. It's adjacent over hypotenuse. All right. So the hypotenuse stays as 10. But the opposite of side x is 6. So don't say 6 over 10 for cosine of x. Say 8 over 10. What about cosine of z? It's the adjacent over the hypotenuse, so 6 over 10. Finally, we look at tangent of x and we look at tangent of z. Tangent being opposite over adjacent. We do not use the number 10 when it comes to tangent, okay? We're using, for tangent of x, opposite of x, which is 6, over adjacent of x, which is 8, 6 over 8. Tangent of z now, opposite of z over adjacent of z, 8 over 6. And before I close, the question, when we come to these trig ratios, because they are brand new at high school level, the question always comes up. Why would we need to use this, and when would we use this? And the interesting thing is, anytime you need to know in a right triangle the angle measure, but you don't have access to a protractor, but you do have access to the two sides, we can use trigonometry. Also, I happen to go to a military college, kind of a Mass Maritime Academy, where we learned how to sail merchant ships across the ocean. And we went from Buzzards Bay, Massachusetts, all the way to Europe. And when you're in the ocean, you can't tell what's what's north, what's south. I mean, the ocean just all looks alike. But what you do is you use trigonometry to map out your journey. And we know that we go 36 degrees for a certain amount of nautical miles, and then we change our path and we do 68 degrees for another number of nautical miles. So please know that you are going to learn about applications for this, but right now we just had to share with you the important essentials about special right triangles and trig ratios.